Welcome to This Explainer, where we're going to unpack the absolute bedrock rules that govern literally every single interaction in our physical world. From the simplest daily chores to the grandest planetary movements, there's a hidden, invisible hand at play shaping absolutely everything we do. So, let's dive right in and ask the ultimate question about the secret mechanics of our reality. What exactly is this invisible power that controls every single movement going on around us? Well, the answer to that massive question really boils down to an incredibly simple yet profound concept: force. In physics, a force is essentially just a push or a pull applied to an object. And when we want to measure exactly how much of this push or pull is happening, we use a standard unit called the Newton, represented by a capital N. To put that into perspective, 1 Newton is roughly the downward force you'd need to hold up a single medium-sized apple in the palm of your hand. To truly wrap our heads around this, our explainer today is going to follow a clear roadmap. We'll start by defining push and pull, see exactly how forces change things, check out contact forces in action, explore the invisible world of non-contact forces, and finally, figure out why things float with buoyancy. All right, let's kick things off with Section 1, defining push and pull. We're starting with what we can easily see and feel. When you think about it, all mechanical effort really just comes down to these two basic actions. Whether you're tugging a heavy rope towards yourself, which is of course a pull, or you're shoving a heavy box away from you, a push, you are actively applying a force to change the state of that object. It really is that fundamental. Moving right along to Section 2, how forces change things. What actually happens out there in the real world when a force is applied? Well, it's not just about getting something from point A to point B. Forces actually do one of four specific things to an object. They can force a completely stationary object to start moving. They can change the speed of an object that's already in motion. They can alter the direction of that motion. Or, and this is super fascinating, they can literally change the physical shape and size of the object itself. You can see these four effects happening constantly in everyday life. Think about kicking a football to suddenly change its speed, or steering a bicycle to shift the direction you're traveling. It's the same thing when you push a heavy shopping cart to get it moving from a dead stop, or when you firmly squeeze a balloon, using physical force to completely warp its shape and size. Now, let's take this a step further. All of these pushes and pulls build into two distinct categories of force. First, we have contact forces. These are exactly what they sound like: forces that absolutely require physical touch between two objects. And then we have non-contact forces. These are a bit more mysterious because they operate across empty space. They act over a distance without any physical connection whatsoever. That brings us nicely to Section 3, contact forces in action. We'll examine these first since they're the ones we interact with most constantly. Every single time you lift a heavy weight at the gym, go for a morning run, or push a wheelbarrow around the yard, you're generating what's called muscular force. This involves the literal physical action of your muscles making contact with objects, or your feet hitting the pavement. It's a prime example of a contact force. And animals naturally use this exact same muscular force to do their own physical work. But here's the catch. Whenever you use your muscular force to, say, push a box across the floor, a second contact force called friction automatically kicks in. As you apply pushing force in one direction, friction is pushing back in the exact opposite direction. Why? Because no surface is perfectly smooth. Down at the microscopic level, they are full of tiny irregularities. When two surfaces touch, those jagged little microscopic bumps lock into each other, fighting any effort to move one surface over the other. Now, depending on the precise nature of the surfaces you're dealing with, this friction takes on one of four distinct forms: static friction, sliding friction, rolling friction, and fluid friction. You see these in action all the time. Static friction is what keeps a stationary wheelchair from just slipping away. Sliding friction is exactly what you experience tearing down a snowy hill on a sled. Rolling friction is the grip between a high-speed tire and the asphalt. And fluid friction? That covers liquid resistance, like a scuba diver swimming through the ocean, as well as the air resistance pushing against an airplane mid-flight. All right, let's shift gears and dive into Section 4, invisible pulls, non-contact forces. We're leaving physical touch behind entirely here. A classic example of a non-contact force is electrostatic force. We've all done this as kids, right? You rub a plastic comb or balloon to create a static charge. Once charged, that object can exert a real physical force from a distance without touching anything. Just look at how a charge cone can literally reach across the empty air to pull and attract little pieces of paper right up to it. But it goes both ways. If you rub two balloons with wool, they both pick up the exact same kind of charge. Because they share a similar charge, that invisible electrostatic force will actively repel them apart, pushing them away from each other. It's a fundamental rule of this force. Opposite charges attract, but similar charges repel. And then, of course, we have the ultimate non-contact force holding our entire world together, gravity. This is the force the Earth uses to attract objects toward itself. Famously, this is the exact force Sir Isaac Newton was pondering when he watched an apple fall from a tree over 350 years ago. Gravity acts on everything, everywhere, pulling it down without ever needing a physical string to do the pulling. Because gravity is constantly pulling objects straight toward the center of the Earth, any vertical motion has to follow three specific steps. If you throw a ball straight up in the air, its speed gradually decreases because gravity is fighting that upward movement. At the absolute peak of its arc, the ball actually stops momentarily. Then it takes a straight path right back downward, its speed steadily increasing as the Earth yanks it back. Simply put, what goes up must eventually accelerate back down. Which brings us to our final topic, Section 5, Buoyancy, Why Things Float. If gravity is constantly dragging everything down, we have to talk about the fascinating force that pushes back up. Enter buoyant force, also known as upthrust. This is a liquid's natural upward push against an object immersed inside it. Gravity is trying to pull the weight of a boat down into the depths, but the buoyant force of the displaced water is pushing right back up against the hull. Whether an object sinks to the bottom or happily floats on top entirely depends on the density of the liquid and which of these two competing forces wins out. This actually leads us to a wonderfully counterintuitive question about our own experiences. If gravity is an inescapable force pulling us down, how is it physically possible to just lie back, float in the ocean, and casually read a book? You can float effortlessly like this because you've achieved a perfect stalemate between two forces. The upward buoyant force of the salt water is exactly equaling the downward gravitational pull of your body weight. Because those two opposing forces are locked in a complete tie, you don't sink. You achieve a perfect invisible balance. Fun fact, this is exactly why it's so incredibly easy to float in places like the Dead Sea. All that extra salt makes the water far denser, which drastically increases the upward buoyant force, keeping you afloat. As we wrap up this explainer today, take a second to look around the room you're in right now. From the gravity firmly planting you in your chair to the friction keeping your device from sliding out of your hand, you are sitting right in the middle of a massive, invisible tug of war. It really makes you realize that even when absolutely nothing seems to be happening, the universe is constantly pushing and pulling in perfect harmony. Which leaves us with one final thought to ponder. If just one of these perfectly balanced forces suddenly blinked out of existence right now, what would happen to our world? Thanks so much for joining me today, and I'll catch you in the next one.